Record on computer then. Okay, and good afternoon, everybody. Please welcome Song Mei from Berkeley, who will talk to us about local convexity of tap free energy and AMP convergence of Z2 synchronization.
Great. Yeah. So thanks for the invitation and thanks for the introduction. This is a joint work with Michael Salatano and Zolfan. So while the statistics motivation is variational Bayesian inference. So in statistics, when you do Bayesian inference, well, in many cases, there is a high dimensional integration, which is computationally challenged. And the variational approach is, well, there are two perspectives. One perspective is that we define some variational free energy and convert the high dimensional integration problem to a high dimensional optimization problem. And hopefully this high dimensional optimization problem can be solved more efficiently. Another perspective is to design iterative algorithms to do the high dimensional integration. So this is the variational Bayesian inference. And this method has been established for more than 20 years. And well, it has been written into softwares and works well in practice. Okay, so well, there are many standard variational inference packages now, and when people do Bayesian inference, they can call these packages. But well, the technical challenge, well, actually this has been developed for 20 years, but theoretically it has not been well understood. The technical challenge are the following. So there are maybe minimizers. Okay, so the minimizer of the free energy, theoretically, people hope that it approximates the Bayes posterior mean. And well, the landscape of the free energy may be not so good. There may be multiple local minimizers, so optimization may not always be successful. And well, if this is an iterative algorithm, whether this algorithm will converge to the global minimizer. Okay, so these are the theoretical challenge of variational Bayesian inference. And today I would like to discuss about a specific high dimensional statistical model, which is called the Z2 synchronization problem. We will study the Bayesian inference in this model and talk about the theoretical guarantee of variational inference. And in this talk, I will focus on the TAP, the tap free energy. This is a free energy originated in the statistical physics literature. When statistical physicists, they study the Shelton-Kirkpatrick model, a spin glass model. Well, they have come up with this TAP, the tap free energy. And well, when they proposed it, it was just a heuristic approximation to the Gibbs measure to the free energy of the SK model. But well, now we want to look at its theoretical guarantee. And well, there is a algorithm which can be used to minimize, well, to optimize the tap free energy, which are the natural gradient descent and the approximate message passing algorithm. I will be more clear what are these concepts in a few minutes. Okay, so let me first introduce what is the Z2 synchronization model. Okay, so it's a statistical inference model in high dimension. We have a high dimensional signal x, x1 from xn, where each xi are +1 -1. Okay, so it's just a +1 -1 bits xi. And we assume that it's uniformly distributed +1 -1. And we don't observe this x. What we observe is the noisy matrix Y, where the ijth element of this matrix Y is the product of xi, xj plus the noise. Here, this lambda is the signal to noise ratio. Okay, and here we assume that the noise are Gaussian. Okay, so we consider the regime where the lambda, the signal to noise ratio, is fixed and dimension n goes to infinity. So in matrix notation, we have a matrix Y, which is n by n, which is a spiked version of a GOE matrix W. And our task is to estimate the signal X given the observation matrix Y. So this is the model we would like to consider. And while we can define the loss function of the estimate to be the square loss, just X minus X hat, where X hat is an estimator of XX transpose. When the signal to noise ratio lambda is less than 1, estimation is impossible. That means any estimator cannot be performed better than 0 estimator. And the phase transition point happens at lambda equal to 1. When lambda greater than 1, estimation is possible and can be efficient. Actually, if you use the spectral estimator, which computes the top eigenvalue or top eigenvector of the matrix Y, such estimator will have non-trivial estimation error. And lambda equal to 1 is called the BBAP phase transition. Okay, but while when you have a prior of this X, this spectral estimator may not be optimal. The optimal estimator is the Bayes estimator, which computes the posterior expectation of XX transpose given the matrix Y. There is a question, why not consider the operator norm? Yeah, good question. So here, for simplicity, we consider the Frobenius norm. But if you consider the operator norm, I guess the answer will not be very different. Because actually, if you look at the Bayes estimator, this will be a low rank matrix. Mm-hmm. And the Frobenius norm is very close to the operator norm, will be very close to the operator norm.
Oh, that holds for the signal, but it doesn't. Wait a second. Like, I mean, isn't it a 1 rank matrix once again?
Oh yeah, X is rank 1. X hat will be also roughly rank 1. So this will be rank 2. But okay, the Frobenius norm and the operator norm will be different.
Okay. So
yeah,
I see.
But it will not be a very. I don't think it will be a very big difference. But well, but you're right. Yeah, it also makes sense to consider the operator norm, perhaps. Yeah, but because another motivation of the Frobenius norm is that actually we want to estimate this X instead of XX transpose. But why here we write XX transpose? Because there is a symmetry. Like when you say X minus X, has the same likelihood as X. Right, so because of this degeneracy.
Yeah, so yes, okay. Yeah, this I understand, but what I don't understand is that why the Bayesian estimator should be low rank. This is not obvious to me at all.
Okay, yeah, this is a good question. The Bayes estimator will not be low rank if you just look at it in this form. But if you work hard on it, we can prove that it's approximately low rank. It's approximately rank 1. So it's not trivial. It's not a trivial claim.
Okay, I see.
Yeah.
So what is the rank, like roughly? Like what are the bounds? Like how much it is low rank essentially?
So
like intuitively why this would be? Could you just briefly explain?
So the rank.
Mm-hmm. So
the rank will be roughly 1. So it can be approximated by a vector transpose. So there is a vector M, where M transpose will be roughly the same as X hat.
It looks like something like the Bayesian concentrate, because
yes, yeah, actually it doesn't concentrate. I mean, the X here doesn't concentrate, but their expectation XX transpose is low rank. This is not a trivial. This is not trivial thing. Okay, and actually we will prove that it's low rank. So, in some sense, this will later will be clear in a few minutes. Okay, so here, let's look at the mean squared error, which is the expectation of the loss of this estimator of the PCA, the spectral estimator, and the Bayes estimator. The blue curve is the error of the spectral estimator. You can see that lambda equal to 1 is a threshold. Lambda less than 1, while the MSE is 1, which is trivial, and then it decays. And the Bayes estimator has a smaller mean squared error than the spectral estimator. Okay, so the question is how to compute the Bayes estimator. Given the observation y, we know the Bayes estimator is expectation x transpose given y. So this is the summation over the configuration sigma transpose, a probability of sigma given y. Okay, so this is a high dimensional summation where the number of terms is 2 to the n. If we just naively do that, that will be 2 to the n times. The computationally will be exponential in n. So we don't want to we want to avoid this exponential in n computation. Okay, so that's the reason why people want to use some approximate method to calculate this Bayes estimator. Okay, so the posterior distribution, if you write it down, it will be just like this. It will be exponential to the power of lambda times the inner product of sigma y sigma over 2. So y here is our observation, which is a spiked GOE matrix. Okay, so this measure, the posterior distribution is very similar to the Gibbs measure of the Kilpatrick model. If you know this, the spin class literature, this is a random measure where the randomness is in y. Okay, and we want to use variational inference approach to compute this posterior expectation. And what is the free energy approach? The free energy approach is that people can find a function f that maps from the solid cube -1 to +1 to the power of n to a real number. And if we say the argument of this function is m, we hope that the minimizer of this function, we call it m hat, it will correspond to the Bayes estimator. Actually, we hope that this m hat transpose will be the Bayes estimator. Okay, so the question is how to find such a function f. The mean field variational Bayes just says that we want to use the mean field approximation. What does it mean? It means that, we minimize the KL divergence of a probability measure, which is a product measure, between the KL divergence between the product measure and the posterior distribution. And we hope that, by minimizing over the product measure, by minimizing each coordinate, the minimizer will be approximately give you the marginal distribution of the coordinates. So if we adopt this point of view, then we can write down this mean field variational Bayes, mean field variational free energy, where there is the entropy term, which is a summation of the entropy of each coordinate mi, where mi, you can think about this mi as the posterior mean of a coordinate. And then there is the energy term, which corresponds to the inner product of m, y, and n. People first proposed this approach, but actually this approach doesn't work well. So people have shown that if we minimize this mean field free energy, the minimizer will not correspond to the Bayes free energy. And 40 years ago, by these three physicists, they proposed another free energy to deal with this model, where this free energy is just adding an additional term. This term is called Einsager's correction term. With this additional term, physicists heuristically show that the minimizer of this type free energy will correspond to the Bayes posterior mean. But this is still a conjecture in physics community and has not been rigorously proved until recently. Okay, so well, what's the technical challenge analyzing this type of energy? Well, first you can see that this type of energy is non-convex. Okay, so if you write down its critical equation, people call the critical equation, the stationary equation, the stationary point of this type of energy satisfy the TAP, the type equation. And there may be multiple solutions of this type equation. So it's not sure, well, the global minimizer, whether the global minimizer is easy to compute and whether it's unique. Okay, so the question is like whether there is a landscape and whether the global minimizer corresponds to the posterior mean, the Bayes estimator. And well, in the literature, people also construct iterative equation that can be used to construct this posterior mean estimator. So this iterative equation is called the approximate message passing algorithm. And the key structure of this iteration is that the k+1's iteration depend on the k's iteration and the k-1's iteration. Well, what people know is that the fixed point of this AMP algorithm corresponds to the critical point of the type of energy. But people also empirically show that while this approximate message passing algorithm will find the Bayes estimator. But well, people don't know like whether this AMP algorithm will converge and whether it's a descent algorithm on the type of energy. Okay, so previously people used a technique called state evolution to analyze the AMP algorithm. So if you start from spectral initialization, well, you can analyze, well, an object called state evolution, which is adopting the mean field point of view and reduce the high dimensional equation to a low dimensional equation. And then you analyze the low dimensional equation as approximate of the high dimensional problem. Using such approach, people can prove such an equation, which says that, well, for fixed number of AMP iteration, as the dimension goes to infinity, well, the approximation error will goes to some constant, and this error will go to 0 as the number of iteration goes to infinity. But while one cannot show that, well, for a fixed instance, as sample size, as the number of iteration goes to infinity, the state evolution, the AMP algorithm will converge to some point that is close to the Bayes estimator. Okay, so the second question we want to ask is whether AMP will converge for fixed sample size as n goes to sk, as the number of iteration goes to infinity. So the type energy and the AMP algorithm are the two quantities we would like to understand better. Okay, and if you do simulation, you can see that, well, this AMP algorithm, and also there are some other algorithms later I will introduce what are these algorithms, they work well. And if you initialize this AMP algorithm, well, in different ways, on the same instance, it will converge to the global minimizer of the type energy, and well, the convergence is very fast. Okay, so empirically, this algorithm work well, but people don't know why. Okay, so our main results just, well, says that, well, first, the landscape of the type energy has a very good structure. It says that, well, if we look at all the critical points of this type energy, okay, so the critical point means that, well, the stationary point, the gradient of the type energy equal to 0. And we look at the critical point for type energy below some threshold. Okay, so then, well, it says that all the critical points are close to the Bayes estimator. So here, this is a claim that, well, here, if this result is true, then, well, okay, this result shows that the Bayes estimator actually is low rank because, well, it can be approximated by a low rank matrix in Frobenius norm very small. Okay, so here this is a cartoon illustration of this result. It says that all the critical points below a threshold are close to the Bayes estimator. So the type energy may look like this, while there may be bad local minimizers above this threshold, for example, here and here. But then for any critical point below this threshold, all the local minimizers are close to the Bayes estimator. Okay, so this is the first theoretical result we established. But while the results are established using the Kac Rice formula, which I will talk about in detail later, but we cannot use this result to exclude, to say that there is a unique global minimizer near the Bayes estimator. There could be multiple local minimizers near the Bayes estimator, but all of them are very close to the Bayes estimator. This is what we can show in this result. Okay, and this year we improve this result to the following. Okay, so essentially in this result we show that while there exists a unique critical point and the local minimizer of the type energy that is close to the Bayes estimator. And this holds for any signal to noise ratio greater than 1, where 1 is the information theoretical threshold. So that means as long as, well, the Bayes estimator has non-trivial power, has non-trivial estimation error, you can find the global minimizer of the type energy, and this is a good approximation of the Bayes estimator. Okay. And also we can show that the type energy is strongly convex near the global minimizer. And the neighborhood, the strongly convex neighborhood is quantitatively large so that it allows some polynomial time algorithm that can converge to M star, and which will be shown later in this talk. So that means, well, by this result, we can show that the landscape of the type energy is like this. Okay, so below an energy threshold, there's no bilocal minimizers, and there is a unique minimizer, which is close to the Bayes estimator. And then there is a strongly convex region, which is quite good. Okay, so, well, this is the landscape result for the type energy. And then the question is that, well, is there an algorithm that can probably find this unique minimizer in polynomial time? And we look at two algorithms. One is the approximate message passing algorithm. People have look at this algorithm in the literature, and it always works, but people don't know why. And then we look at another algorithm. We call it the natural gradient descent algorithm. This algorithm has a very interesting interpretation, which is that, well, it's just the gradient descent on the type energy, but it's not a gradient descent in the Euclidean sense. Well, it's a Bregman gradient descent. Okay, so, well, you can see that while the connection of the natural gradient descent and AMP is that if we take the step size eta to be 1, then, well, the natural gradient descent is very similar to AMP, except that here K in the natural gradient descent only depend on the Kth iteration, whereas the AMP algorithm depend on the K-1 iteration. Okay, so, well, first result shows that, well, actually a hybrid algorithm will converge to the global minimizer in polynomial time, actually in very fast. So we show that, well, first we run AMP. So what's the hybrid algorithm? We do spectral initialization, run AMP for T steps, and then continue to run the NGD algorithm with step size eta. For this algorithm, one can show that as long as the lambda is greater than the information theoretical threshold, well, this algorithm will work, will converge to a global minimizer, well, actually exponentially fast. So there is for each k, the error decays exponentially, exponentially in k. Okay, so this says that if we do spectral initialization, run AMP and run NGD, it will converge to this minimizer exponentially fast. Okay, so the intuition is that we can use state evolution analysis to show that this approximate message passing algorithm will converge to the local region, where the local region is a strongly convex region. And we can use the strong convexity, actually the relative strong convexity and relative smoothness of this function near this global minimizer. Use this information to show that this NGD will converge. Okay, so this is a nice algorithmic result. People may ask, so now, because it's a mixture algorithm, it's a hybrid algorithm, right? So can we show that individual AMP or individual NGD algorithm will converge? Okay, so we can show that when the signal to noise ratio lambda is large enough, then both AMP and natural gradient algorithm will converge to a global minimizer. But this requires the signal to noise ratio is large enough. And I think this condition is because we don't have a technique. We did this is due to the restriction of technique. Okay, so what do we know about AMP algorithm when lambda is just greater than 1? We only know that what we can show is that M star, the global minimizer, is a asymptotically stable fixed point of AMP. That means there exists a small neighborhood of the global minimizer. If AMP initializes in this neighborhood, it will converge to the global minimizer. But we don't know how large is this neighborhood. So this delta may depend on n. And as n goes to infinity, this delta may converge to 0. Okay, so this result is not good enough to establish the global convergence of AMP. So an open question is that can we show the spectral initialized AMP will converge as long as the signal to noise ratio is greater than 1? Okay, so here are some simulation, and in this simulation, what I would like to show is the universality of the problem. So the proof and the problem we stated are upon the Gaussian random noise. But actually, if you have Rademacher or other mixture kind of noise, this algorithm and the landscape are also nice. Okay, so here are just some universality results which shows that if we change the noise to be Rademacher or mixture, the curves doesn't change much. Okay, so I would like to briefly talk about the technical challenge of proving the landscape results of the type-free energy. Okay, so the technical challenge is that, we didn't work in the large signal to noise ratio regime. Okay, so the large signal to noise ratio regime is that, lambda also grows with n. In such regime, you can show that, even the spectral estimator will be consistent estimator. So in that regime, you don't need to care about whether you use spectral estimator or the Bayes estimator. And in that regime, also something good happen, which is that the empirical risk will converge the population risk uniformly good. So the population risk is the expectation of landscape, and the empirical risk is just the loss function we want to minimize. And when the signal to noise ratio is large enough, one can establish the uniform convergence of the empirical risk population risk, so that the empirical risk minimizer will be close to the population risk minimizer. Okay, so this is what people can show if signal to noise ratio is very large. Well, but the problem is that in this model, the signal to noise ratio is not large enough. So what happened is that while the empirical risk minimizer is far away from the population risk minimizer, this is because no uniform convergence will happen. And the location of the empirical risk minimizer will be a random location. The randomness comes from our observation. So it's very hard to establish, well, the landscape result for a random objective function, and very hard to establish the local landscape result for a random objective function. Okay, so the technical tool we use to calculate, to analyze the landscape of the type energy is called a Kac Rice formula. So the Kac Rice formula can be used to compute the number of critical points of a random Morse function. Okay, so for our target function, so for our objective function, well, because of the randomness of the noise we have in the matrix observation matrix, while the function is random, and well, because we assume the Gaussian randomness, so actually the target function is a Gaussian process, and it satisfies this random Morse function condition. Okay, so using Kac Rice formula, it tells us that the number of critical points of the type energy for the critical point in some specific set can be computed using this formula. This formula is the integration over the set, and there is expectation of the absolute value of determinant of the Hessian, conditional on the gradient of the target function equal to 0. And then this PM0 is the density of the gradient equal to 0. And the integration is over the points in this T set. The difficulty to deal with is to deal with this determinant of the Hessian. So here, the determinant of the Hessian, well, we need to compute the absolute value and then take the expectation. Okay, so what we, well, but although it's like, well, you think it's maybe technically involved, but actually, well, because the nice structure of, because the Gaussian assumption we made, the Hessian of the type energy will be like a low rank perturbation and a diagonal perturbation of a GOE matrix. So the low rank perturbation will not contribute to the determinant of Hessian by much. And well, what you only need to deal with is actually a diagonal matrix plus a GOE matrix. And we can use some tool in free probability to calculate this determinant of Hessian so that we can deal with this term. We can deal with the expectation of determinant of Hessian term. For the density of the gradient, this term is very easy to deal with. This term can be written down explicitly. And finally, we use Laplace method to deal with this integration. What we can show is that, well, the log expected number of critical points divided by n, the rate, is upper bounded by some rate function s. And supermum over this q, phi, and e, well, these are some order parameters. Well, supermum over these order parameters in this set U. Okay. So that means, well, after we establish these upper bounds, what we only need to do is to analyze this S star function to upper bound the number of critical points of the type energy in some particular sets. Okay, so here we plot the S star function. And actually here I plot the one-dimensional projection of this S star function. And this is a complex, we call it S star the complexity function. We plot the complexity versus the energy level E. Okay, so we can see that, well, so the energy is below this threshold when you look at the left-hand side. While there is only one point of this complexity that touch 0. For any other place, the energy, the complexity function is below 0. So that means that, well, the energy, when the type of energy is below some threshold, well, there is only a unique energy that can have non-zero, that can have critical points. And by analyzing this complexity function, well, because we have an analytical expression of this S star, well, it's a function of Q, V, and E. By analyzing this function, we can show that all local minimizers below some threshold are close to the global minimizer. Okay, but well, through this method, we cannot preclude, well, any other local minimizers near the global minimizer. Okay, so to deal with this difficulty, we need to introduce another tool, which is the conditional Gaussian comparison inequality. Okay, so what we want to analyze is a Gaussian process. What is a Gaussian process? Well, we want to analyze the Hessian of the type energy. And well, we want to look at the eigenvalues of the Hessian, the minimum eigenvalue of the Hessian when the when our variable, when M is in the close to the global minimizer of the type energy. So the inner product of U, the Hessian U, this is a Gaussian process. We want to look at the extreme value of a Gaussian process. But the problem now is that, well, this M star is a global minimizer. It's not a deterministic point. So we cannot directly apply this Gaussian comparison inequality. But, well, we can say we conditional on this M star is a global minimizer. Actually, we conditional on M star is a critical point. Then this gives a Gaussian, this gives a equality constraint of this Gaussian randomness. So actually, conditional on this equality, well, this part is still a Gaussian process because of the Gaussian conditioning formula. So this is actually the Hessian conditional gradient equal to 0 is a finite rank perturbed and diagonal perturbed GOE matrix. Okay, so while using a Gaussian comparison inequality, well, it's actually a Slipian inequality. We can show that this rescaled Hessian is lower bounded by some variational formula. And we can analyze this variational formula to show that, well, the rescaled Hessian is greater than 0. Okay, so that means while using this conditional Gaussian comparison inequality, we can show that, well, the type energy will be locally strongly convex near the global minimizer. Okay, so there are some technical challenges showing this lower bound. One challenge is to control the empirical distribution of the coordinate of M star. Well, we need to use the Slipian plus Kac Rice formula to give it a tight control. And another difficulty is to analyze this variational formula. You can see that this is inf soup of some variational formula and the inf over the primal variable, soup over the dual variable. Well, to handle this, although it's an analytical formula, we have a formula for this H, but analyzing this requires some technical work. Okay, and finally, well, we need to give a union bound because here, using the conditional Gaussian comparison inequality, what we are showing is that, well, for any local minimizer for any points near the global minimizer, the Hessian is convex. But then you didn't figure out where is the global minimizer. So we need to give a union bound over the global minimizer. And it's hard, we cannot directly use the epsilon net argument to apply the union bound. Well, we need to use the Kac Rice formula again to obtain this union bound. Okay, so this is the third technical challenge in this proof. Okay, so this is the technical step used to analyze the landscape of the type energy. And well, then we want to discuss about how to analyze the algorithm. Okay, so for the convergence of natural gradient descent algorithm, it's just due to the geometry. Okay, so it's just due to the relative smoothness and relative strong convexity of the type energy versus the entropy term. So this is a pure geometric result. As long as we show this geometric property, this implies the convergence of natural gradient descent algorithm locally. So for the convergence of approximate message passing algorithm, what we need to analyze is the operator norm of the linearized AMP operator. Recall that AMP in the AMP algorithm, the k+1 iteration depend on the kth iteration and the k-1 iteration. We can rewrite this AMP algorithm as an evolution of the concatenated k+1 and mk vector. So as long as we are able to show that the operator norm of the linearized, the Jacobian of AMP operator is less than 1, conditional on M star is a global minimizer, then this can imply the global convergence of AMP. Okay, so we are able to show the operator norm bound of AMP, the Jacobian of AMP operator, when lambda is very large, well, larger than some constant, whereas we can show the spectral norm of this Jacobian of AMP is upper bounded when lambda is greater than 1. So this result imply the local stability of AMP algorithm, and the second, this result imply the global convergence of AMP. Okay, so let me summarize the talk. So in this talk, we have shown that a type energy has no spurious local minimum below a threshold, and it is strongly convex near the Bayes estimator. We show that a hybrid algorithm, or hybrid spectral initialization plus AMP plus NGD algorithm can converge when signal to noise ratio is greater than the information theoretical threshold. We show that when both of these algorithms will converge when lambda is large enough, and AMP is asymptotically stable at M star. And we believe that this proof strategy can be extended to other high-dimensional inference problems, including generalized linear model, including the Kac Rice model, including a few other models. So this is all I have to talk about today. Thanks for your attention.